Today we will continue our topic on searching the web with search engine ranking and optimization. These are actually two topics and do not follow each other. Basically, they are different views on the same problem of ranking. So search engine ranking is a general technology or general method of combining multiple partial rankings that gives us or give us some subsystems, and we need some final ranking for the user. While search engine optimization or SEO is methodology for users or for the content creators, how to create the content in order to rank well based on the ranking of a search engine. So we'll look from two sides of the same problem. The ranking, the first topic, the ranking from the side of search engine is based on, of course, a ranking function, because ranking function is an aggregation function that takes the partial rankings coming out of the partial results that the system gives us, and then creates the final ranking. This could be done either in one step or in multiple steps. In the one-step ranking is the classical approach to providing the aggregation, and is mostly implemented using the top K operator. And for this operator, there are two famous algorithms called Fagin and threshold algorithm. In the multiple step ranking, there are very many methods how to provide final ranking using some greedy strategy that is called re-ranking. So we start with one major ranking, then cut irrelevant, non-relevant results, re-rank the rest, again cut non-relevant, and so on until we get some small final ranking, and this was consecutively created using multiple objective functions. And the second part is the user view part, or the creator view part, and that's the optimization of content. That's called search engine optimization, and it's about, basically, it's a reference manual or some methodology, some recommending best practices for creating content. In our case, creating web pages, but it could be creating any content that is presented to users and at the same time is indexed by some search engine. Okay, when starting with the first one, we already have seen basically two types of ranking. We had experience with the vector space model, which is basically content ranking, or it provides content relevancy of the documents, the web pages or the content, with respect to a query. So we need a query and we get some ranking based on cosine measure and the bag of words or vector space model. Then we also saw how to compute PageRank, which is another ranking of content of web pages that measures kind of popularity or reputation, or this query independent scores of web pages, and there could be others like layout based ranking. We are searching maybe for some business documents, and there it matters how the document looks like, so some kind of layout is involved, and so on. So we can generate, or we can obtain, many kinds of rankings based on different objectives, and we must finally get just one ranking for the final user to be presented. Such as in Google, we also get the final ranking, no matter what are the underlying partial rankings inside of the search process. What are the basically factors that could be associated with the ranking? we have already discussed the query, of course, the content itself, the text, the structure, the graph information. That's why PageRank was created. But there are many more. For example, the author or user that creates the content, or even a company or a corporation. When just focusing on user, the user could be modeled by the user preferences that could be inferred, for example, from search history the user performs, different access patterns, products bought, for example, on eShop, and so on. So the user is some background knowledge for the search, and it's a context that we can use. So that's why we are also talking about personalized search. We will talk about this some future lectures. The structural context is associated with the application and with the environment. In the easiest environment is just collections. There is no context. But the next step towards a greater context, structural context, is the graph. So web graph was very low level context that involved the structure of the web graph. And we could continue to more sophisticated structural contexts like social sites, social media, where we don't only have the edges and the nodes, but we have users, we have objects like posts, comments, likes, and these objects that basically are not involved in the basic web infrastructure. But we could, of course, use this knowledge, because the more knowledge, the more abstract knowledge we have, the more effective the search could be. And of course, some interaction or behavioral context, like how other users are behaving, interacting with me or with the inspected user, and so on. So there are many factors that contribute to relevancy when searching, and all of these could be used for partial rankings that need to be aggregated, as I already discussed. So, in short, the final ranking could be done in one or multiple steps. In the one step, it's the classical approach. We have some global ranking function, aggregation function, that takes all of the rankings and transform the partial scores into global scores, and that's it. That's providing the final ranking. Or we can do the greedy algorithm, as I said, do consecutive re-ranking of partial ranks using some changing criteria and using the ever-reducing set of candidates that came out of the previous step. And of course, there are many specific other rankings that are subject to competition, are basically disclosed. Okay, because the one-step ranking was studied earlier than the web was so famous and omnipresent, basically the whole technology and the formal definitions are not based on web pages or content, but they are basically related to what was known 30 years ago and was relational databases. So instead of ranking objectives or scores or partial rankings, we would have just real valued ordered attributes A1 to AM, and just we will think about content entities as of records in a table. So we have classical relational model, we have database, we have a table. The rows of the table are the entities, like web pages in our case, and the columns in the table are different classes of scores. That's the attributes. And of course, we would like to take the tuple, m tuple of the attributes to somehow provide the final score. That's why there is aggregating function f defined that takes the m tuple and provides some real valued score. And what is required is that just simple property that f should be monotonic function. So monotonic in this multidimensional context means if I have two values, one value of the partial score and then another value from a partial score, then when I apply these two scores that are one greater than the other, then the overall function, aggregating function, that only replaces x for y, also this change reflects that the first one is greater than the second one. So this is the monotonicity based on just individual components of the function. All classic simple aggregating functions satisfy this constraint, like minimum of values here, maximum, average, anything basically that is linear combination. Yeah. So it's very very broad class of aggregating functions. Also, we need to unify the meaning of the attributes to be easy to work with all of these attributes, and it's, for example, good to state or to define the attributes that their higher value means better value. So we are considering the scores the same way for all the attributes, and so we can sort them the same direction and so on. So let's have this convention that better value is higher value, and the model could be adjusted this way. For an example, we already discussed the vector model, so we have cosine similarities of web pages with respect to some query. That generates first ranking. The second ranking could be some layout of web pages. I said I search for business documents, not for poetry, for example, even that they share similar text. Maybe that's a bad example. Business documents and poetry probably do not share anything. And the third ranking is the page rank. So we have three partial rankings with the same content. So we have 6 web pages, and this set of 6 web pages is sorted 3 ways. First by content, by cosine measure, second by layout, and third by page ranks. And we have different rankings. You can see that we have different scores and different rankings because the set is sorted with respect to the scores. So the first one is the best one with the high score, the last one is the worst with the lowest one. And the aggregation function, in this case average, sorts the rankings into one final one based on the aggregation. So we take just averages of the partial scores and we get the final ranking. So in this case, the P4 won. It was 0.81, 0.91 and 0.37. Altogether in average it's 0.7, and this is, in this trade-off, it's the best. So the second one is P2 and so on. So we get P4 as the winning web page, even that it was winning just in the second layout similarity, and it was not winning either in the content similarity nor the page rank. So we can really shake the order when taking multiple partial rankings. Okay, so how to implement this? Okay, of course, we could do just very naive implementation. As I said, just compute the overall scores for all of the objects in the set and then just sorting it. But this is naive and needs to process the whole set, which could be really large, could be billion of web pages, and we need to take many times these sets because we have different orderings, and this is very slow and it's not scalable. So the top K operator is a database operator that basically implements this naive aggregation procedure in more efficient way, and this efficient processing is could be realized by different algorithms. We have two classic algorithms that implement the top K operator, and that's the fagin and the threshold algorithms. Actually, they are both authored by fagin, and maybe the fagin name for algorithm was not very lucky, because then the threshold algorithm came and basically was proved to be better than fagin. Not proved to be better, but in realistic situations it's better, but it's not clearly better. We'll see. So the question is, how can we sequentially basically implement the top K operator? And let's have this running example. Again, I repeat, this is formalism based on relational model. So we, instead of web pages, we have just objects, IDs, like elements, but for us these are web pages, A, B, C, D. And instead of partial rankings, we have attributes, attribute 1 and attribute 2. So let's say this is cosine similarity and this is page rank, for example. And we have this relational table and all the rankings for all the objects. And now we need to process the top K operator. For this, we need all of the rankings to be to provide the sorting with respect to the score. So this cannot happen in table. We have the sorted just the attribute 1, like here, but the second one cannot be in the same table sorted the same way. So we need to split the table into so many smaller tables that is the number of attributes. So we get one sorted list, basically second sorted list, no more table, just list. And to not lose the basically record, we need some pointer from entries in the first list to the entries to the second list, and maybe to the third list, and so on. Depends how many attributes or rankings we have. So we see that these 0.9 for A is connected with 0.85 with A, and so on. We have also backlinks here, so we can basically really quickly reconstruct the rows from any entry here and any entry here. Of course, it will be for the cost of random access, because we don't just read everything at once, as we are used in relational technology, but we need to really jump somewhere in disk or to memory, wherever it's stored. And in the running example, we will have minimum aggregating function, and of course we have the interpretation that the higher value is better, so that's why we have the highest values on top. So for attribute 1, the A is the best. For attribute 2, A is not the best because there is 0.9. So in the sorted list, we have the individual best rankings on top and in the descending order. But here is A, here is D. So now we need to process all of the list to obtain the top K answer, so to implement top K operator. And the first algorithm for this is the fagin algorithm, that is composed of two phases. It first reads all entries from all of the lists in parallel, so it goes one by one in all of the lists until the algorithm retrieves some K objects, all of the ranks. So for some of the objects, they are all partial ranks known. In this case, we have basically K candidates for the top K operator, and in top K operator we are searching for top K, so we need K objects. And in this first phase, we get some of the K objects, not the final one, but some of them, so some candidates. And now, once we have the candidates, so we know for some K objects all of the M ranks, then we basically retrieve for all other objects that we already saw in some aspect. So we have read some scores, but not all of them. So we basically access randomly all of the remaining ranks in the lists. So we get all the ranks for all the objects that is at least k objects. We have k objects, for k objects all of the ranks, and for some of them we just saw a few of them. So for these where we have saw just few of them, we determine the rest. That's the second step. And then it's very easy. Then we have enough data to compute the aggregations. So we compute the aggregations, sort what we have already determined, and return the top k objects. So in the example, it's easy. Let's have k set to 2. So we are searching for top 2 ranked objects. So what we do in the first step, we read the first in parallel and second, so first and second in parallel. We get 0.9 for A and 0.9 for D. We keep some buffer or some temporary structure that we store here the intermediate results or the scores, partial scores, and we read until we have some k. Let's see, k is 2, so let's have some 2 objects read using the parallel scan that determines all of the scores. So we don't have yet. So in second step we have all scores for A, but we introduced 0.8 for B, so we need to read more. And in the third we have already 2 complete entities with scores. So A and B are complete. And we have also D just for just A2 for D and just A1 for C. So now it comes into play the second step when we need to determine the remaining scores for the incomplete entries like D and C, so these 2 scores. And that's how we use the random access. For D we get 0.6 and for C we get 0.2. So now we have all scores for at least k, which is 2, just 2, so we have more than 2, we have 4, and we could compute the aggregation function, which is for this case minimum. So we get 0.85, 0.6, 0.7, 0.2, and just pick the best scoring two objects, which is A and B, and this is the result. So this is the result that is presented to the user, and the algorithm ends. The second implementation is the threshold algorithm, and it was basically introduced later. So the Fagin was first, and the Fagin algorithm was observed to be not optimal with respect to the parallel scan, because in some bad situation we can basically scan the whole set in just the first step. So it's completely not efficient, because in that case it is just full scan. So the threshold algorithm uses different strategy. Instead of splitting the algorithm to 2 serial steps, it does the 2 steps in parallel. So it does the parallel search and immediately random access to load or to determine the missing ranks. And now we need to redefine also the stopping condition that we had different in the Fagin algorithm. And in this threshold algorithm, it will be a threshold. That's why the algorithm's names. And the idea is the following: the objects are being read from the best scoring to the lowest, as in the Fagin algorithm, but immediately after each parallel step, we determine the rest of the rankings for what we have already saw or what we already seen for one value in the ranking, for one score. And so we keep updating the aggregations. So we do not compute aggregations after some number of steps, but immediately. So immediately we have the candidates for the top K objects, and we only update the best score seen so far and the threshold, that is the basically best score that could be seen after the position that we have already processed. So what could basically be below this line? Best. What could be best below this line? In this partial settings, it could be 0.7 because it's this for C and B, but we have already processed this. And once the best ranked score for what was already seen here is better than the threshold, so the possible theoretical value that could be seen below this line, then we are done, because that there cannot be nothing better below this line that we have already seen, and the algorithm stops. So this is the idea of threshold algorithm. And again, in the running example, it looks like here. It looks like this. Again, we begin with parallel reading, step 1. So we get 0.9 for A and 0.9 for D. But instead of proceeding in parallel one line below, we determine the remaining scores for A and the remaining scores for D. We have just two because we have just two lists. And we get value 0.85 and 0.6, and we immediately compute the aggregation function. So we have basically two candidates now for top K result, and the best one is 0.85 and the second best is 0.6. And if this 0.6 is better than we could ever get below this point, then we are done. But this is not the moment, because now the threshold is defined as 0.9, because we are in the parallel reading, we are still here. Of course, we have determined something from below, but in the parallel scan, we are still here. So theoretically, below could be something with the overall score that is 0.9. We see that it's not true, but from the algorithmic point of view, it could be. So now the threshold is still higher than this 0.6, which is the kth best score, because we are looking for the top two operators. So we have 1 and 2. So the second one must be better than this threshold, and then we are sure. So it's still not true. So we must continue again with parallel reading of the two lists. So we go down and we observe B and A. So for A, we already know everything because we already saw it in list 1. So now we see it for the second time, but now using the parallel scan instead of random access. And now what's new, we see B. So B we fetch into the table 0.8, and we must immediately determine the second ranks, which is B for the A2, and it's 0.7. We compute the aggregation, which is 0.7. Now we have 3 candidates, but we search for 2 objects. We have top 2 candidates, top K, K and K is 2. So we have 3 here. So we don't need the worst anymore, so which is D. So we just delete D, and B is the new second candidate. And we continue. Again, we determine the threshold, which is in the next line, which is in this case 0.8. But so it decreased from 0.9 to 0.8, so it's going down, the threshold is going down. But the second best scoring object is going up. So it was 0.6, now it's 0.7. So it goes up and this goes down. Okay, so well, but we still cannot stop because 0.7 is worse than theoretically 0.8. So we need to go one more step down. We retrieve C because B was already retrieved. Now the threshold goes down for 0.7. We must of course determine the value for C, which is 0.2, and that's why it's overall scored 0.2, so it gets out of the ranking. So what we already have is that we have met the threshold, which is 0.7, and the partial second best score, and that's the moment when the threshold met the real result and the algorithm could stop. So these were two algorithms, Fagin and threshold algorithms, and now some discussion. So both of the algorithms are correct based on the monotonicity of the aggregation function and of course sorted lists. All of the lists are sorted, so we are going down and only can see worse scores as we are going down in each particular list, and because of the monotonicity we cannot any aggregations of these decreasing results could be only also decreasing. The properties of these two algorithms. The threshold algorithm basically reads less objects than the Fagin algorithm. As I said, the Fagin algorithm could really get bad in the parallel scan, so it could read the most of the database. The threshold algorithm updates more frequently, so it's more demanding on the reading, but for the cost that the threshold algorithm really performs more random accesses. That's also obvious because what the Fagin algorithm reads in parallel, the threshold algorithm, some of this could read in random. So of course parallel reading is cheaper than random access, but when it's two of the parallel reading, then it's even worse than the random access. So that's the motivation for basically threshold algorithm. So this is one trade-off. It sees threshold algorithm sees less objects, but for the cost of random access, which could be better or worse, depends on the situation. But what is clearly better for the threshold algorithm is the bounded buffer space, because we only keep updated the top k candidates for the operator, but the Fagin algorithm uses unbounded buffer. So again, in the worst case, it could really expand to the size of the database, and that's really bad situation. So this is about the properties of top k operator, which is one-step ranking. In the multiple step ranking or re-ranking, basically, we use multiple step ranking in situation when the one-step ranking is too expensive or is difficult to implement, or the use case is difficult to solve with one-step ranking. We must also think, if we get back to the example, the algorithms are defined on the relational case. So we have just table and we have random access to table, blah blah blah. But in the environment of web, this is ranking. This is not a table, and the ranking is basically, it could be a stream that is downloaded from internet incrementally. So we don't see all the data or the whole column as one object that is at the moment available, but this could be just a stream, and we have different streams. Here list 1, list 2, two rankings, two streams, and it is clearly but it follows similar similar advantages, because in relational databases, a parallel scan is cheap because it reads the data continuously from disk, so it doesn't need random access. And the random access means expensive operation on the disk. But this is similar to the scenario with streams, because when we read in parallel streams, it's cheap because we are already getting the stream information. So there are no delays in reading, because what we see on the top is really what we get from the stream. But if we need to get randomly positioned information, for example from here to here, or better from here to here, we basically cannot just do random access in stream, because the stream is stream. I cannot say, okay, get me this. Okay, I can do that, but that would require some additional effort on the side of the provider of this ranking. But what can I do is to wait. Basically wait until the stream goes down here and I can read this. So there is some delay, and this is the slow interpretation of random access in case of streams. Okay, so yeah, and for some algorithms or some use cases, this streaming and aggregating is not feasible. So a better solution could be multi-step ranking. So we have one ranking already determined, as for example with one stream, and once we have it, we could re-rank by some other criteria of what we already got. So for example, we have ranking based on cosine measure with respect to a query, and then we can re-rank a fraction of this result with respect to page rank, and return to the user just the top scoring in both of the rankings. Okay, so the result is clear. We don't do any aggregation of the scores. Basically, we just process it sequentially. So we do not aggregate like averaging, minimum, whatever with the scores. We just take first ranking using some ranking function. We have sorted list of candidates. Then we take just a smaller prefix of this ranking, and this smaller prefix goes to the next step, which is again taken as a database, re-ranked, some smaller prefix is taken to the third, and so on until we get small enough prefix, and that's the result. So this is really multi-step ranking. Okay, so in our example it could look like this. We have sorted functions, ranking functions. The most important is, for example, sorting by content similarity. So we get this initial ranking, we take smaller prefix of the ranking, so just these 4. Take these 4, re-rank them by page rank, just take 2, and these 2 re-rank by layout similarity, and that's the final score. This could be an example of very simple re-ranking based on 3 objective functions, but the most important one is the cosine measure. That's why it's first, because in the second step we cannot retrieve any of these P1 and P5, was already discarded because we just took prefix of length 4. So it really matters what is the first ranking and what is the second. This didn't matter with the top K operator. It was symmetric, but here it's no more symmetric. Okay, and basically that's just very slight introduction to ranking, top K operator and re-ranking. And now we look on the second aspect of ranking, and that's the user point of view, or basically the creator point of view, the content creator point of view. So search engine optimization. We didn't care much up to today how the content is created. We just assumed we have some content somewhere stored or streamed or something, or crawled by the search engine. but we didn't care about the origins of the content. Now we care about the origin. So if we are now the creators of the content, how can we ensure that the content is so quality and so good that it will rank high in the ranking, in all of the rankings? So we must consider many of the partial rankings, like the information retrieval models, like cosine, similarity or vector model, PageRank, and whatever other ranks. Maybe some popularity, personalized rankings. We'll talk later about recommender systems and so on. So we have now multiple objectives or multiple concerns about the content quality to get the content high ranked. And this is what search engine optimization is dealing with. First of all, it is a bit a confusing name, because search engine optimization suggests that we will optimize search engine, but that's not true. We will optimize the web pages or the content to be well ranked by search engine. So it's basically optimization of content for search engine, not really optimization of search engine. So that's a bit confusing, but once it's clear, it's clear. Okay, what it is good for, and is it important? Well, yes, because there is a huge competition of resources or content on the web. We have billions, trillions of web pages, and all of them want to rank high in Google. Basically, on a query that is relevant to billion of documents or of search of web pages, all of them want to be the first, or at least 1 in 10 best scoring. And it's obviously not possible because there is a tough competition. And of course, what does appear on the first page of search engine is also successful in business, because the web pages are not just toy problems. They are bounded to some business, and of course this is a huge business behind the SEO, the search engine optimization. Everybody wants to get high scored. So it is extremely important to perform SEO for web pages in order to be successful on the global scale. Okay, this is some funny slide, and it only emphasizes the need for good ranking, because it says that the best place to hide a dead body is the second page of Google search results. That's basically the motivation for SEO. Nobody, or at least or mostly nobody, sees the second page of Google search results. Many people even don't see the bottom of the first page. So it's really important for everybody to get on the top few scoring results. But for us, it's basically not a technology. It's some soft skill methodology of creating web pages that really go or follows the assumptions that the technologies do about the content. So it's basically about fitting the content to the technology, basically methodology. There are clear connections, so it's not completely isolated from technology, but it's basically some recipes to be compatible with the search engines, more than just a technology. There are no algorithms, nothing. But okay, there is a thesis. As we have thesis for PageRank, we have also thesis of SEO, and the thesis is really natural and simple, and just says, a content of a web page or a resource that is good to human should be good also to machine. So it basically must, because the effectiveness in the sense of data quality is the central objective function for both for SEO and for the search engine ranking, and both share this common concern. So for SEO, it's a good message because SEO cannot really dig into some guts of search engines because they are really classified. But it's enough to really be honest and optimize the content to be good for humans. This should be enough because the search engines also have this objective to return a content that is good to human. So let's not manipulate anything and just do good stuff. That's basically the thesis. And it is connected with the ethical issues. The thesis is connected with ethical SEO. So we don't want to manipulate the content of web pages. We are not pretending something that is not inside, but we are just augmenting the organic content of the web pages or the resources for long-term SEO effect. That's basically what also the thesis wants to do. And the second unethical SEO bet, that's basically the manipulation. So we can insert some content just for manipulation in order to get better ranks by search engines. But this is really short-term effect, and it's more sooner or later discovered by the search engine and penalized. So that's unethical SEO. And of course, it's a business, as I said, because good page ranking means successful business. And yeah, as businesses are nowadays moving more and more to internet, this is basically critical part of the marketing and of communication. So SEO is really necessity for businesses. Okay, now how the augmentation, as I said, could be done. So there are many facets of optimization, and of course we stick to web pages. We do not optimize anything else but web pages, but of course we must think more general. So what we are now talking about web pages could be applied for other media like PDFs or social media entities. So optimization of web pages and optimization of posts on Facebook, for example, basically follow the same. And we must keep in mind the thesis of the SEO, and it doesn't matter if it's for web pages or for documents or whatever. We are creating content for humans, so we have the same goal, whatever kind of media. And technically, for web pages, we will just briefly discuss how it could be done for web pages on the really raw level. So what we can identify in a web page source code, on HTML code, we could see different tags. Of course, there is also file name or URL for the web page, and so on. We have the hypertext information, we have the links, we have also images embedded, and so on. So all of these structural elements are involved in the SEO because they matter something for humans, so they must also matter something for SEO, and also the search engines recognize them as more or less important for the human. So let's start with a single web page. We are doing optimization for single web pages, not whole sites. But of course, a whole website is optimized just by taking many optimized web pages. So the whole site is in the end optimized. And if you have the very lowest level entity, so web page, that's one file, which is HTML, PHP, whatever. And the first we have is a file name or URL. So for example, for this web page, we can see that in the URL we already saw in the file name the terms that we search for. So we search for information retrieval, and we see that there is information retrieval directly in the file name. So we even do not need to download the file and parse it. We we see it already from the title. So that's really important aspect of optimization, to really optimize even the file name itself. In this case, it's the second place, of course. But on the first place, there is also information retrieval in the file name. Yeah, there are some technical conventions, like okay, the hyphens are spaces, but it's not really important. The second most important element that needs to be optimized is the title tag of HTML, which basically is just a little less important than the file name, and this basically says what is the whole page about. So the keywords that are inside the title basically are just summarizing the whole document. So that's why in the search engines and in also human minds, because we must think this is interconnected, or should be, they get really high score. Information retrieval is definitely more relevant pair of terms than, for example, area of study, like here, because area of study is just in full text, but what is really important is in title text, so information retrieval. There are some technical, again, specifics, like because of the presentation by Google, which is up to 64 characters, it should not be longer than these. So, because more than 64 characters doesn't show up. So this is something that should be taken into account, but it's the primary ranking factor. And then we go down in the hierarchy of elements that are less and less important, but starting at H1, which is header 1, so the largest header that we have on the web page, that's the most important. For example, web search engine is the most important. It's about the web page, and basically it's also the title, also the file name. So just follows this semantics. And then H6 basically is the least important. Here we have H2 for history, like here, and H1 for web search engine. There are also meta tags defined in HTML documents, which could be user defined. So we have meta element that could have whatever name, there is some description, and whatever value. And this was meant basically as a substitution for what we already had in relational databases, that was database schema. Here in web pages we don't have any schema, it's just really unbound format for presentation of information. So to be at least really minimize, to have at least some minimal notion of structure or content, we could use meta text like name and using name and value. So we can define keywords, description, and so on. And this should be somehow reflected by the search engine. But basically nowadays this is not used, because it could be misused. Of course, as everything could be misused, because basically the unethical SEO is connected with this. In unethical SEO, you can define meta text for content that is not present in the actual content. So that's basically spamming just for the manipulation, just for the ranking. And that's not really what should be done. Okay. We can have other meta tags, like as I said, keywords, or for example robots, that say to the search engine what to do with the content, if it's appropriate to index this content, or it's just technical, for example hub or something that doesn't have any information, and whether to follow or not the links inside this content. So this is something more helping the search engines, not much about SEO, not much about augmenting the content, more than helping the robots. But it's not also used much There are nowadays better tools how to help robots navigate in the web graph. It's better to put the information about the navigation outside of the HTML file, not putting it here, because in the file there should be content, not navigation. So not mixing two completely different instructions. And we get down to text that emphasize text, which is strong, emphasize, bold, italic, and underline. So it's just modifying a bit the text, so making it bolder and so on. So again, it has some meaning for the user, not that big as header or title or so, but still it's emphasized because it's something more important than just regular text. So the World Wide Web is more important than, for example, commonly known. So for this reason, it's good to use emphasizes for the text. And again, in the ranking, these terms should be weighted in cosine model or vector model or whatever model, more important than the other non-emphasized keywords. But of course, this is just intuitive interpretation, just on the human-centric basis. Other content than text or HTML code is the embedded content, which is mostly images, videos, and other multimedia or applications. And for images, for example, of course they are not parsed, or there is no OCR put on the image to extract text, what is inside. It could be done, but it would be extremely expensive. Instead, it's good to provide some text also for the image, not only to the file name. Of course, the file name again is important here, but also to the alt attribute, which is alternative text for the image, which was basically introduced in the begins of web for slow connection, because if 30 years ago you had slow connection, it would be extremely lengthy to download this image or any image. Some text-based internet browsers just use text information, and this is the text alternative to image. So there is some connected graph in this image. You can see there are many connected graphs, and in this moment we can use this text not only as an alternative text description, but as a basically description for search engines. So this connected graph is the same keyword representation as we would use for the object that is inside. So that's really handy to use it. So image optimization. And of course, the other huge part of the optimization workload is optimization of links. And first, what we can do is optimization of the easier, and it's outlinks. So that's the links that are inside the content that we are managing. So we are managing this content. This is again Wikipedia web page, and there are many outlinks. You can see relational databases is href, some link, title, and we can have the other is World Wide Web and so on. So we have many outlinks, and for outlinks is again important to be well structured, well distributed, and so on, to not produce basically spam. For example, if every keyword here is an outlink, it would not make sense. So there must be properly dense distribution of outlinks. That is not manipulation. And that's how the statistic improve, because then the page becomes a hub, as we were talking last lecture, and hubs could be really useful and create basically inlinks for other pages. So that could be beneficial for all of the pages that are in the graph. Okay, so there are some rules where to put the links. Links at top positions are more important than the bottom ones, because the text is also important on the top than in the bottom. Links in a block of text are more important than isolated ones, because they are in context, while the isolated ones are not, and so on. There are some this is really more intuitive than rule-based reasoning about links. Okay, so outlinks. Well, outlink as a link is just link, but we still need the keywords, and the keywords are the most important elements in SEO. So whatever location of the keyword, it's important to properly select keywords. So keyword generation and distribution within the content is extremely important. So how this could be done in some 3 steps. Of course, there is some organic content on the web pages, so there is a limited set of keywords we could use. We cannot use agriculture keyword for a web page about the Linux system, of course, but still, within these limitations, we still could do some optimization. First, we need to analyze the potential impact of the keywords, and for this there are many web-based services for keyword analysis. So let's start with analysis, because it's good to know whether a particular keyword has a theoretical chance to basically be used by users for searching or not. Then after this analysis, we must basically select a set of appropriate keywords that is really organic for our content, not to really act as manipulation, because we need to augment the content, not to manipulate the content. And then put the selected keywords into right places, again in some organic way, not to be really visible as manipulation. So in terms of the class of keywords, we can distinguish between generic keywords and specific. The generic are called tail terms, and the specific or the head terms, and the specific are tail terms. So head terms and tail terms, as the title suggests, have different cardinality of the target group of users. So the head terms means they are generic. So we must have some generic keywords that basically attract a lot of traffic, so a lot of users, but these are also highly competitive, because everybody does this. Everybody starts with head terms and uses really generic keywords to attract more users. So in addition to head terms that are not so specific, we must add some more specific ones that are called tail terms, and they really focus our content into something that is more specific, that of course generates less traffic, because less users are interested in more specific topics, but there is also less competition. So we must basically combine a mixture of these two types of keywords to get the right blend of keywords. For example, here we have racing. We can have any kind of racing, but specific keywords means, for example, old cars racing, which is really specific, more than just racing. Generates also less traffic. There is no Formula One, and that's how basically the specialization goes from abstract to specific. Yeah, and then there's, because we have these two kinds of keywords, head and tail keywords, we also need to carefully place them in right places. So the high competitive keywords, the head keywords, are good to be placed on the main page, because the main page is the one that everybody sees when it comes to downloading your page, and this really generates the traffic. And on this page was just really the was really the page that was attracting everybody, but we must really be aware of that most of the users that come to this main page will not continue on browsing the pages in the site, because that's how it works. So main page was really interesting for anybody, or it pretend to be interesting for anybody, or not pretend but appeared to be interesting because it used the head words. But then the users will see, oh well, this is a page about all cars racing, not about racing, so most of them go away. But it is important to put the competitive keywords on the main page to even attract the wide audience to see the page, because without this nobody will come on the page, not even the people that are interested in all cars racing, because there is no base to be selected users from. So we need to really start with head keywords, and then once we have the audience, we need to focus to the audience that is really interested in all cars racing. So we'll use the tail keywords and really keep the users on the page, the right users on the page. Of course, the others will go away. Okay, so the focus basically at the end is on the tail terms, because that's the value that could be or should be promoted on the web page, because the page is about the tail terms. It's not about the head terms, right? So there is a business concerned about old cars racing, not about whatever space galaxy racing. So it should focus on tail terms. Otherwise, everybody go away. Okay, so this sequence of usage of terms is important. And I didn't mention, but the whole SEO process is not one shot or one attempt task. It must be continuous work, because not only the topic of the business of the page changes, but also the context changes, the users change, the trends change. So many aspects change. So it is really important to keep the SEO process in work, because also the statistics on keywords change. So what was a popular keyword 2 months ago is not a popular keyword now. So there must be reanalyzed the keywords and updated the content and so on. So basically this is a never-ending process, the SEO process. As I said, for analysis of keywords, there are many applications that could help to select the right set of keywords. There are many of them, but they are basically obsolete. You can see this is quite old survey on them, but basically it doesn't matter, because there are many of them and they have specific functionalities. For example, the key compete here could be used for find out the best traffic sites for a certain keyword. So if we have a keywords information retrieval, again, we get these 5 best scoring sites that basically users search in these sites stuff for the keyword we entered here. So for example, Amazon/books is the best scoring site for information retrieval. So who searches for information retrieval probably searches for books at Amazon, and there are also other services. Or we can use it the other way around, so we can find the best keywords for a certain site. So, for example, what is the best keyword or highest traffic keyword for Amazon, for example. We can show it on different surveys, which is keywordspy.com, and for Amazon, as I said, we can see that of course there are some artificial keywords like com, because it's just domain free, but the fourth, basically the best keyword that means anything is DVD. Okay, well, DVD is quite obsolete, but yeah, that's almost 10 years old. And then books and music and cars. So we can see what Amazon is successful with, and we can see the volumes of the accesses and traffic changes and whatever. Okay, now generally the creation of content. As I said, the content should be created organically, so the web page must describe its real content, not just some artificial augmentation. So we write primarily for people, not search engines. We use proper keyword density. We also use latent semantics. That's also quite important issue. We do not use simple ways to create content, so we do not duplicate content. And as I said, we keep the content current, up to date, and to really demonstrate that it's living. And we optimize also non-HTML documents, because these are part of CO2 and are downloaded and parsed by the search engines too, like PDFs, for example. The writing for people is basically following the basic thesis of SEO. So basically that is what I said. What is good for a human is also recognized by the search engine. So let's avoid poor grammar, for example. Let's write natural, persuasive, original content. Use style of writing that is interesting, that is not machine appearing, some generative or something. It's also good to consider multi-language site, not just one language, and so on. So basically, the recipe for using SEO is this simple. Just write for people and format for people and structure for people to be as useful as possible. The keyword density is a factor that we already mentioned, and okay, we have the head terms, tail terms, but the frequency is also important, because it's directly connected with the vector model of information retrieval. And as we have discussed the TF-IDF weighting, we need to use keywords that are really specific to the document. That's how the keywords get really high TF component and small IDF component of the TF-IDF. That's basically the tail keywords. But in this respective content, we also need basically stop words, or not stop words, but something that is more towards stop words, because this is something that generates the traffic. It doesn't basically act as the final subject of the topic, but it attracts the audience. So, for example, that's why we were discussing racing and old cars racing. Also, okay, racing has quite low IDF, because it appears on many web pages. So it basically could be viewed as a almost stop word, not stop word, but really very frequent in all of the web pages. But it attracts the audience for this really high level term. But then the tail terms, like old cars racing, this whole combination of keywords, then acts as the one that is really important, and that really keeps the audience on the web page. And all of this is reflected in the vector model. So in the vectors that come out of the web pages when using cosine similarity, really reflect the distribution of keywords, because they count the frequencies and they are specific patterns. So if a user expects a specific pattern of keywords that the user expects, then the page that really follows this distribution will also score as the best, at least in the content-based ranking. So the keyword density and vector space model are highly connected. Latent semantics, again, what we have discussed in vector model, and it's connected with the richness of the language and the style of the text. It's good to really use related keywords, semantically related keywords. So it's not only about the richness of the language. For example, in times where Obama was a president, then it's good to use both of the terms. And it's not only for better style of writing, but it's also for a danger of over optimization that could be detected by the search engine. If we still use president, then the search engine could detect, oh, this page really wants to highly weight the term president, and this is somehow odd. So it's better to, and it's not natural. Again, it goes against the organic nature of the content. So it's good to use semantically related keywords using broader set of terms. Okay, so this has the connection with latent semantic indexing. We have also mentioned in vector space model, but here from the content creation point of view. And of course, creating duplicate content is always bad practice for anything. It could not be directly plagiarism, but it at least is just demonstrating, okay, I don't want to bother with creating my original text. I will copy myself, for example, or just do general introduction to some web page or something. And this, of course, is identified by the search engine and is penalized. Let's eliminate duplicate content. And the last thing about content creation, general advices, is to keep the content current, up to date. As I said, everything changes in the environment of web. The web itself changes, the people change, the trends change, businesses change. So there are many factors that just really motivate to get the content up to date. Optimization for non-HTML documents, as I said, PDFs or some Office documents. These all are parsed by the search engine, so they also need to be optimized the same way as web pages. So we must look at the non-HTML document as HTML documents. Of course, not images or not documents that do not provide machine-readable text, but still, but for these that are machine-readable text, there must be done optimization. Another concern when optimizing web pages is optimizing the whole website structure. Of course, just on the level of web pages, because we don't have element like a website, we have just web pages. But if we consider the web pages as a set that belongs to a site, we can do many things that basically go in the line of the optimization of the whole site, not just the individual pages. So design of a website is the first of concern. This is not about optimization. This is basically about the design itself. So when we are creating website, we must do design of the website. It's not just for SEO. It's for the design itself. There is a good practice to use sitemap and robots files, as well as company information and htaccess file for the robots. So the design, of course, this is kind of outside of the scope, but it's still important also for SEO. So the first most important thing is choosing the suitable domain name. Of course, it must be short, recognizable, and really bound to the subject of the business or of the content. So if we have really keyword in the domain, then this is a huge gain. The whole site must be built around some thematic structure, and again, this is organic content, because the whole company or whole content of the business is built around some thematic activity. So also the website should follow this. This is nothing special. Establishing, of course, the hierarchy of internal links. So using outlinks, we can create basically the site. The site is defined by the links, by the internal links, not by some high-level entities like site, but by linking the web pages. This is how the site is recognized then, by human and also by the search engines. And of course, we must avoid broken links, error messages, and everything that is basically bad design. Sitemap is a file that helps navigate the robots over the site. So in this sense, it's a help, but it also helps to basically create good structure, good semantic structure of the website. So it's not only a technical help for robots, but it's also semantic help for the design of the website. Then robots.txt is basically a file in the root directory of web server, and just says how to the robots what to crawl and what to crawl not, how to save bandwidth, and so on. Basically, this is kind of obsolete. It's better to use the htaccess file for this. Another good practice is to provide not only the content about the subject of the website, but also about the background, about the reputation, about the company. So there is, of course, PageRank somehow measures the reputation, but this is just information extracted from the web graph. We can put more on top of this reputation site by stating that the company has some information privacy policies and so on, and has a structure in the business world, and has these ethical rules and whatever. So it's a good practice to provide this information as a general information on the website. Nowadays, everybody must click on the rule about using cookies, for example. So this is one enforced practice that must every page provide. But there are many other good practices that the pages state something about themselves to really notify the users what will happen with their data that they are putting into the page. And the htaccess file, as I said, is a file that is not just one. It's basically, it could be done for every site, and just can guide the bots, the robots, to download something and follow something else, and so on. So this is more customizable than the robots.txt. And last, and the most important part and most difficult part of SEO is basically building the backlinks, the inlinks. We already discussed building the outlinks, which is easy because outlinks are inside our web pages, but getting inlinks, this is something that is out of our control, because we cannot alter other web pages than ours. So it's a slow, difficult process to get many inlinks, and in this way to boost our PageRank score and to get higher scores in the overall search process because of higher PageRank. So how to do that? There are some ways how to create backlinks or inlinks. And of course, you must have a partner for this, because somebody else must link to your page. So it's about building some social community of linking partners, and of course, searching high quality partners. And in the last resort, there is also buying the links, but this is expensive and basically sort of desperate way how to create backlinks. It's better to participate in some community and optimize on social media or like on social media. So getting into a community in order to basically join a graph that is not just web graph, but it's more than that. It's some community graph, and this is how the backlinks must be done in general. Technically, we can use again some services that could provide us domains that is good to have a backlink from, because they have large PageRank and will send a piece of the PageRank to our site as well, because that's how inlinks work in PageRank algorithm. So we can see, for example, Alexa, which are the high traffic pages, and acquire links from these ones. We can use other tools like domain tools. We can try to obtain links for highly respected sites like Edu or Gov or others, and so on. So there are many ways how to target the linking partners, and then to negotiate with them, as I said, creating the community. There is this clear connection to PageRank, as I said. Finding a few high quality links is better than having a lot of low quality ones. That's because of the PageRank formula. We can easily count or compute how the contribution is when considering on few high quality or a lot of low quality links. Okay. Requesting of one-way links is a not so good way how to create inlinks. It's some old-fashioned way, really writing emails, really handcrafted building of inlinks by even phone, but it's probably not happening anymore. And it's a really difficult and time-consuming way, but it could be effective because you are creating some really personalized communication. It's not just spamming. You are investing some time and personalized information in this process, but it's really slow process and not guaranteed to work. Of course, depends on your skills. The better way is community participation, because it really shots many birds with one stone, because it's not only about creating backlinks. It's basically that you really need the community participation regardless of any backlinks. If you are running a business that is in some context of other businesses, and it serves some users, some clients, you probably want to communicate with the clients at least, or the competitors, and this is something that creates the community, and this is also the basis where backlinks can be generated. So community participation is basically it's basically really important, especially in the time of social media. It's basically a must-have component of the PR, to have some social media profile and to promote the product or the service, or just the content. This is what I said. And technically, social media optimization is really connected to SEO, because it's a part of the SEO, and now it dominates SEO because it's really effective to promote content by social media, because nowadays social media is so large infrastructure that it basically overrides for example, Google or traditional search engines, they are a group of users that use, for example, Facebook search really more than Google, because Google is basically too complex for them, and they are okay to live just on Facebook. So why don't to use just the search in Facebook? So for many businesses, the efforts for SEO just is limited to social media optimization, and it's enough, because it attracts much more traffic than would attract the traditional web pages. It's case of many businesses and many organizations that they have really high traffic Facebook profiles. The last way how to get backlinks is buying. Of course, this must be a good idea when linking from really high PageRank scored web pages that are otherwise not reachable by community collaboration and so on. So the last thing we can do, if they offer this option, is to buy the links. There are some broker networks for buying links for some money, but basically this is not a good practice. For example, Google criticized this practice of buying links, because basically it's a kind of spam, because if you are buying something and do not try yourself, you're basically doing some expensive spam. Good services for analysis of web pages are Google Analytics. So there could be a piece of code put in your web page, and then just see analytics on top of the traffic on your web page. So it's good to see the life of the web page in terms of accesses to the web page. And also Google Webmaster Tools serve a similar reason. So you can search for queries, links to site, keywords importance, errors and crawling, and so on. So there are also nice graphs, and you can observe statistics on top of a web page. And the last thing is unethical SEO. As I said, unethical SEO is short-term SEO. You want to quickly manipulate and quickly get highly ranked, but you don't use legal or ethical tools to do that. So it could be some spam farms. You can spam many keywords into your content, so the spam or the keywords do not appear because there are some metadata, but they try to fake themselves as being highly relevant for any query, basically. Or they have many inlinks that are generated by link farms. Again, this is to boost the page rank, but again, this is short term, because these link farms are to be more, sooner or later discovered as spam farms. So it will ban or penalize such a page that uses this unethical SEO. Okay, so misusing keywords, spamming keywords, and basically manipulating the content. I think that it's clear that what's the point about this whole topic. Okay, so we are done. There is many other books about the topic of search engine optimization and ranking, of course. So if anybody's interested, just search. You can start with this classical books, for example, Modern Information Retrieval, some latest edition, and there are many more questions on the subject of SEO, and many more problems that are to be discussed. So that's all from today.